So the history of our understanding of our solar system and universe, I find really interesting personally. How way back, long time ago, it was believed that the Earth was the center of the universe and thus the solar system, which makes it makes sense if all you are doing is observing that the sun comes up in the east and goes down in the west every single day. It's really kind of interesting to hear the things that transpired over many years. As far as what we need for this class, though, we're going to talk about Kepler's laws, and this goes along with orbits. So Kepler was someone who worked with an astronomer that had very careful note-taking is not the right word, but observation, very specific observation equipment to make note of where planets were in the sky. And Kepler was able to use the data to come up with they're considered laws now. So his 3 laws. The first law is that all planets orbit the sun in ellipses, meaning they're not perfectly circular orbits. That was one thing that was held on to for a very long time, is that the orbits needed to be perfectly circular, and observations did not support that. And so there's some interesting things that were made up along the way to try to explain this. The second law, essentially the easiest way to think about it, it's not the way he states it, is that planets move faster when they are closer to the sun. So just a little exaggerated picture. So elliptical orbits, meaning the planet at some point in time is farther from the sun and some points in time is closer to the sun. This is highly exaggerated. The planets themselves, their orbits are not perfectly circular, but they're fairly close, so they're not actually this exaggerated. Kepler's second law is actually called a law of areas. If I draw a line from the sun to a moment in time where the planet might be. So here's our planet. In a set amount of time, the planet may have moved this far in its orbit. There is an area that is traced out in that time. Kepler's second law is telling us if we do the same thing and just look at a later moment in time, the area swept out between these 2 lines has to be the same. The area swept out here has to be the same as the area swept out here, which, in order to have a smaller r, we have to have traveled through a larger portion of the circle. In order to do that, the planet must be moving faster when it's closer to the sun and slower when it's farther away. This is what his second law is stating, is this equal area. We will explain this also in terms of equations, in terms of conservation of energy. Energy is conserved. And so we will describe this in the next video in terms of energy. The third law is that the period of the orbit squared is related to the radius of the orbit cubed. Now, what we mean by period: the amount of time to complete one orbit. We use a capital T to mean period. So lowercase t has always been time, but it's whatever time we were talking about. Capital T is a specific amount of time. It is specifically the amount of time to complete one orbit. And so he found that this period squared is directly related to the radius of the orbit cubed. Now, to correctly account for elliptical orbits, we would need to think about center of mass and all this sort of stuff. We are going to use a circular orbit approach to just look at this basic relationship. So we found in the previous video the speed of the object in a circular orbit depended upon the mass of the planet or whatever was being orbited, and r being the radius of the orbit. Well, if we think about a perfectly circular orbit, the speed will be constant, which means we could say it's a distance over the time. So one complete orbit would be a circle. So the circumference, the distance traveled in one complete orbit would be the circumference of the circular orbit divided by the time it took, which is what we're calling the period. So I'm going to equate these right here, and this is going to allow us to relate this period to radius of the orbit. Now, the first thing I want to do is square both sides so I don't have to deal with the square root. Now, if I bring t squared over, this r comes up and gives me r cubed. And then we have g and m in here. This is the simplified version of Kepler's third law. The period squared is related to the radius cubed. This is assuming a perfectly circular orbit. It becomes more complicated if we are accounting for the ellipse. But as far as what we're going to do, we're going to just look at this perfectly circular orbit. Now, as a reminder, what is this m going to be? So capital T is the period, meaning the amount of time to complete one orbit. R is the radius of the orbit. The distance from center to center. M comes from our speed equation. This is the mass of the object being orbited. And this equation can be used for the space station around the Earth. It could be used for the moon orbiting the Earth orbiting the sun. In the case of it being elliptical, it would be an approximation. But this equation is in the test notes, by the way. We can use it. You do not need to derive it again. But Kepler's third law is great at relating how long it takes to orbit to the radius of the orbit. It was actually, Kepler's laws were not fully, well, they weren't laws until Newton came along with his universal law of gravitation to mathematically show all of this to be the case. But they are considered Kepler's laws. They are very commonly used in astronomy. I want to do one example using this Kepler's law, and then we'll move on to energy. All right. So let's look at this problem. In recent years, astronomers have discovered thousands of planets orbiting nearby stars. These are called extrasolar planets. Suppose a planet is observed to have a 1,200-day period. I'm just going to write this over here. As it orbits a star at the same distance that Jupiter is from our sun. So I need to go to the table in the test notes and find how far Jupiter is from the sun. All right, so looking at the test notes, it tells me on average, Jupiter is 7.78 times 10 to the 11th meters from the sun. We're trying to find the mass of the star, and then how does this compare to the mass of our sun? All right, anytime, as far as we're talking about this gravitational stuff, that we see a period and radius, we want to just jump to Kepler's third law. So period squared is equal to 4 pi squared r cubed over gm. G is our constant, which has units of newtons, meters squared per kilogram squared. R is in meters. M is going to be the mass of this star that we're calculating. In terms of units, I always get asked what units period needs to be in. Well, if we think of all the units that are going to be on the right side of the equation, the 4, the pi squareds, those aren't units. They have radians embedded into it, but again, not true units. R is in meters. G, Newton meter squared per kilogram squared. M is going to be in kilograms. The time is within the newtons. If you remember, a newton is a kilogram times meter per second squared. In order for our units to work out, our period must be in seconds. Okay, which, that's fine. One day has 24 hours. 1 hour has 60 minutes. A minute has 60 seconds. So our days cancel, our hours cancel, our minutes cancel, and this will be the period in seconds. Which is a big, huge number. I'll write it up here. Lots and lots of seconds. Okay, well, to solve now, we're looking for the mass of this star. So I'm just going to rewrite our equation. And then we can plug in. Okay, so R is to be cubed G. All right, so I'm getting 2.59 times 10 to the 31. That will be in kilograms. We can follow that through if we want. The R is in meters and it's been cubed. G is in Newton meter squared per kilogram squared. And time is in seconds, which is squared. A Newton is a kilogram meter per second squared, which we have divided by kilograms squared. So the meters are going to cancel, the seconds squareds are going to cancel. One of these kilograms cancels and gives us kilograms. Very large mass. But to put that in perspective, that's where question B comes into play. How does this compare to the mass of our sun? For example, if I just divide this mass by the mass of our sun, the mass of our sun, again from the test notes, that 1.99 kilograms. If I divide that, I get 13. This star is 13 times bigger than our sun. Our sun ends up being pretty small when we look at all of the other stars that are out there. This is quite a bit bigger, but again, in terms of being able to detect extrasolar planets, the ones that are being detected are on the larger side as well. Let's do one more example, actually. You'll see a note about geosynchronous satellites in the test notes. Our communication satellites, our GPS satellites, are considered geosynchronous. And they need to be. What that means, the prefix geo is essentially Earth. Earth, we know, rotates on its axis. It's actually tilted, but that's not important to this question. As the Earth rotates on its own axis, the satellite maintains its location above the same point on the Earth. So if we were looking in the sky, the satellite would look like a star. It would always be in the same place as far as we're concerned. That means the period of orbit is 24 hours. The Earth rotates on its own axis with a period of 24 hours. What I would like to find is how high above the surface of the Earth must a geosynchronous satellite be? So remember, in terms of orbits, the speed of orbit is always directly related to the height at which the radius of the orbit is what I mean. So because I'm relating in orbit and talking about period, I can go ahead and pull out Newton's third law. So I know the period. M here will be the mass of the Earth because that is what is being orbited. So again, I'm pulling that off the test notes. G is our constant, which is also on the test notes. It's both within chapter 13 and it's on the front cover as well. The period we will need in seconds, which that's easy enough to do. An hour is 60 minutes. A minute is 60 seconds. So the minutes cancel, the hours cancel. And we find the period to be 86,400 seconds. All right, so r cubed, if I bring the g over, the m over, divide by 4 pi squared, to get rid of the cubed root, or the cube, just as a reminder, I can take both sides to either the cubed root, or that's the same thing as taking both sides to the 1/3 power. My basic calculator doesn't have the option to do the cubed root like this, and so I have to use to the 1/3 power. So I will put everything in and then take to the 1/3 power like this. One of the common mistakes is forgetting to square period, or cubed radius, or squaring pi. So typically the mistakes are on the basic side, just forgetting to do one of the basic math operations. Make sure to write out what you're doing when it comes to a test, so I can see if there's a basic misunderstanding, just an error on plugging stuff in versus not knowing how to set up the problem. Another, just FYI, be sure to have the 4 pi squareds in parentheses when you plug it into your calculator. That's another common mistake. Okay. I don't like writing all of this stuff out because we don't know it this significantly. But I'm not done yet. The question is asking how high above the surface of the Earth. R here is the radius of the orbit, meaning from the center of the Earth to the satellite itself. So if we want to know how high above the surface, h is going to actually be this radius we just found minus the radius of the Earth. So from the test notes, radius of the Earth, at least on average, 6.37 times 10 to the 6 meters. So I'm going to take the answer I just got, subtract off the radius of the Earth, and I am going to round my answer because I need to. I don't know anything to the accuracy at which my calculator is giving me. 7 meters. That doesn't make any sense. Oh, yes, it does, because that was to the 7th. Sorry. So a geosynchronous satellite is 3.6 times 10 to the 7th meters above the surface of the Earth. Just out of curiosity, when I look at the conversions on the test notes, 1 mile is 1.609 kilometers. So to convert this, just to put it in terms of miles, my brain understands miles better than meters. If I divide exponent 3, that's approximately 22,000 miles. Quite a ways away, of course. So next video, we will look at energy and solve some problems using the concept of conservation of energy.